So, good afternoon to all the candidates and good morning to Professor Imre. So, Professor Imre is already here, and without taking any further time, I'll request him to start his today's lecture. So,
Thank you so much, and good morning, good afternoon, good evening to everyone, depending on when you are staying at this very moment. Today, we will have two lectures. Between the two lectures, there will be a break. And the first lecture is about the typical functionalities and enabling computing technologies of next generation cyber physical systems. So let's go into the first block, which is titled Functional Description of Cyber Physical Systems. And let me start with a kind of explanation, clarification on this concept of functionality. So the cyber physical systems are in evolution, and the functionality, what they implement, is very much changing time to time and from system to system. So we can say that there are so-called generic or definitional functionalities of these systems like sensing, searching, communication, networking, computation, conversion, actuation. But the major issue is how it is implemented and what sort of resources are used for it. Because, for instance, analog hardware, digital hardware, control software, application software, alphanumeric dataware, and semantic knowledgeware can all consider. So, if we want to characterize a next generation cyber physical system for functions, then we have to abstract it, because the function actually, or the functional view, is actually a abstract view on cyber physical system. The functions are potential operations typically formulated in an abstract manner considering requirements. Functions are not yet operations, but functions are derived from the requirement, and functions are converted into operations, no matter if it is mechanical, physical, chemical, or whatever type of operation. And when this operation, which is modeled actually in a system, is executed by a system under permanent or changing environmental conditions, that is the behavior. So, sorry for this. I make a difference between functions, which are potential operations, operations, which are the concrete operations, and the behavior, which is an implemented operation. So abstraction is crucial since systems of high complexity cannot be designed and managed on otherwise.
Imre,
yes,
have you not shared your presentation?
I'm sharing my presentation.
It's not visible. It's not visible since the beginning.
Really?
Yeah, that's why I bothered to stop you actually.
Yes, please. Thank you so much. But I set it just a moment. Yeah, it is share screen is on.
So please stop the share screen and share it once again, because
sorry, maybe it, okay, I did it and now I'm sharing.
Yeah, now it's coming.
Okay, sorry for that. I wasn't aware of it. So then this technical issue, sorry for that again, because I pushed the button and I saw that that it goes on. So these are the first side, the functional description of cyber physical system. That was the first or the second side, slide, in which I connected the general functionalities to the certain kind of general function carriers, and I started to talk about the functional abstraction of systems. And obviously, when we consider the needed abstraction, we can say that various levels of abstractions can be used in model-based design and also simulation-based validation of cyber physical systems. it has been recognized that every system has specific functions, but they can be clustered and abstracted to a set of generic functions. The major question is, and the major knowledge for us to know, what belongs to this generic set of functions for next generation cyber physical systems. So, as I said at the beginning, functions are transformed into concrete engineering operations, and they appear as observable physical behavior. And every cyber-physical system implements only a particular given subset of cyber-physical functions according to the purpose and the objectives what it has been developed. So typically, we talk about composition-oriented functional structures, which allow the architecting of the systems and not only the specification of the operation of the system. So I would like to use a concrete practical example to show you how we abstracted, how we generalized the functions of cyber-physical systems. And towards this goal, I would like to play a new movie to you. This movie is running. I would like to mention that one of my PhD students called my attention to this particular movie, which is developed by and recorded by Japanese colleagues and shows a cyber-physical operating theater. You can see what we have here, but I stop not to disturb you in following the movie. Just please confirm, can you see the movie?
Yes, sir.
Thank you.
Is there some sound also in the movie?
Yes.
But sound is not audible.
No problem.
Okay.
Later on, I will explain a lot of things. No?
Yes, now it is audible.
Excellent. The reason why I said that actually the sound is not so important because it was in Japanese, and more important were the English subtitles, what we could use there. And then thanking to the Japanese colleagues one more, we believe that operator theater is really reflecting the overwhelming majority, if not all, generic functions of cyber-physical systems. And then let's go through this. So with the question in mind, what are the main functions of this cyber-physical system? The first one is related to the interfacing of humans and systems. And as you could see, the system is a human in the loop system, but it also manifests as a system of systems and the wide area network system. The second is the ambient and internal sensing. As you could see in the movie, the system has various general ambient sensors as well as specific medical sensors such as MRI scanner. The next one is the web-based data and tool gathering. So you could see in the movie that the system interconnects several data processing tools and also collects and transfers data from and to the web. Powering of the system is also an important aspect because the system has a context-sensitive power management subsystem for robotic and visualization devices. Then the distributed digital computing aspect, which was explained by the professor colleague, that the SCOT actually a multi-actor system which is based on real-time and distributed high-end computing. We will talk about this in the second block. Managing network is also a functionality, and the actor nodes of the system are not only locally interconnected, but also connected to the internet. So locally connected and connected to the internet. Signal and data transmission and communication. The system is located at the Hiroshima University. Now, initially, it was also initiated by the Tokyo Medical University, but is geographically distributed over the internet. Monitoring and controlling is also a generic function. The human control and supervision activities are supported by all embracing visualization and failure avoidance functions as well. Semantic reasoning, it was mentioned that the system contributes to the decision making of humans and prevents misconduct and provides advices to human actors. Then data and big massive data analytics and mining, it was explained by the professor colleague that in addition to visualization, which is the main communication channel in this environment due to the intensity of the visual communication, the system also extracts operation information and records and analyzes activity and status data. And then providing infrastructure, you have seen this sophisticated robotic environment. And the explanation related to that is that the system is equipped with many assistive devices that are remotely controlled by humans and supervised by the system. Actuating the physical effectors is also a major functionality. The system is equipped with various high-precision robotic arms, effectors, and manipulators. Providing services, it was also shown that in addition to operation support, the system provides knowledge sharing, archiving, and advising services. Then the next one is converting sensations. It was explained that the dominant conversation mode is visualization, but haptic and tactile sensation conversion is also appearing and practiced in the system. So these are those sort of functional elements which we could extract from this particular system, obviously considering the functional spectrum of other systems as well. And we have developed a kind of overall functionality model of next generation cyber physical systems, which builds up in the following way. First of all, we have the internet and ambient sensing, interfacing stakeholders and systems, web-based data and resource acquisition as a kind of input side. Then we have a kind of processing side on which the powering of the system constituents is happening, the complete cyber physical computing is implemented, the network operation management is practiced, and system resources are provided. Additional system resources can be also considered. Then on the output side, we can identify something like smart reasoning in context, big or massive data analytics and mining, and controlling and planning adjustment. And then we have a other side, which is about the supporting functionality, for instance, signal and data conversion and transfer, actuating physical processes and devices, conversion of sensations, and providing stakeholder services as much as it can be at all. So we can see that the overall functionality of a next generation cyber physical system can be decomposed into four categories. One is the category of the functions which belong to the observing. The second category is that group of functions which are belonging to processing. The third one, those which are actually having reasoning in their core. And then the next one is actuating, which is related to the interaction with the real world and the cyber. So this is our model, we use, for instance, with our students in order to provide a functional description, or later on, if the system is already known, a kind of functional characterization of the system. And the major issue, and this is what you may ask, this model is very informative. It is most probably useful, but how to use it? Because actually this is just on the generic level function, and it doesn't extend to the lower level function. But actually, this is the task of the functional design, to decompose the highest level, we refer to them as main functions, into component functions, and consider the hardware, the software, and the cyberware elements which are needed to realize that particular sub-function. So this is behind the methodology which we propose for using this functional model. And we say that if you want to make functional modeling for all relevant main functions, what you identified according to the previously shown diagram, for all or each of the four categories, ask the following. Do I know one or more functional careers that implement this function as a whole? And then obviously the answer can be yes or no. If the answer is yes, it means that you found that you were successful in finding a function carrier which provides that particular major function what is required. But typically it is not the case. It might be, but not always the case. If it is not, then you go further. Then you have to ask as that, do I know one or more function carriers that partly implement this function? If the implementation is partial, that it means that if you have such function carrier, then you can select and use that for two reasons, as a starting point for extension, or you may adopt it. But if not, then you have to go deeper and you have to decompose the main function into sub-functions and sub-functions, as I said earlier, with regards to the hardware and software and cyberware. And then again, the next action is that to ask yourself if you know one or more function carriers that partly implement this sub-function, no matter on which level of the sub-functions you are. And then if it is yes, then you can say that select and integrate that particular low-level function carrier in order to provide the higher level function. If not, then obviously you have to develop and integrate that hardware and software elements which implement it. And then since in this sort of top-down process, we have to go through uh, all of the main functions, and main functions will be converted into sub-functions and even elementary functions, for instance, which are realized by a particular algorithm of a software. Then you repeat it until the whole system is functionally defined and can be used for the next step, as I explained yesterday, for the architectural design. Obviously, when you have the functional carriers, these are the components, the modules, and the higher level structural compositions of the system. So what I was talking about and what this particular functional decomposition methodology is based on a hierarchical decomposition. It is well known from the German functional design, which literature pile bags were very much supporting this sort of approach. Now it is a kind of revitalization in the context of next generation cyber physical system. Uh, Before going further, let me mention a couple of things why we believe this particular model is important for us. First of all, it is a more focused capability specification than the traditional matter, energy, information concept. I mentioned the traditional PI-BATS approach, which is also based on the Rodenacker approach. They are talking about matter, energy, and information flow. But it says that the already existing solutions are not directly addressed and not considered. This is why we believe that our functional new function and purpose-oriented functional modeling is more relevant. Obviously, the model what I mentioned captures the major generic functions, but I also mentioned that no matter what complexity we are facing, we can decompose it. And this way, it can be a starting point of a hierarchical decomposition, which extends to all hardware, software, and cyberware system functions. So this particular functional view on the system is integrative because it is proposing or propagating a kind of holistic view. And um, this functional modeling allows the identification of the extent of the CPS nature of the system. So how much it is really CPS? What are the cyber physicalities there? How it is appearing in the function? And this is also a very important issue for the system developer, especially when, for instance, the aspect of smartness are to be considered. And this model, what I was talking about, lends itself to a kind of conceptual framing of the functional design, and it can also considered as a kind of scientifically based methodology with all the methods and with all the instruments, computational instruments that can be used. And obviously, it is also paving the way to architecting of the system. And we believe that it is a practical advantage, especially for the industry, that function carriers can be searched for on multiple levels, for instance, on system level, if it is possible at all. In case of a system of systems, it might be interesting, but definitely on subsystem level, on unit level, or module level, or component level, and so on and so on. And obviously, if we forgot about something which is a important generic feature of a next generation cyber physical system, or new functions emerge, then this particular model can be extended with alternative functional capabilities, and we may claim that actually this model follows the evolution track of cyber physical systems. So far, it is so good because it is an important tool in the hand of the system developer to make a correct functional specification. But obviously the architecting comes later on. We will talk about it. We will talk about, for instance, the model-based design and the component-based implementation and so on. We also will address the organization of the computational human interaction and so on processes. But there is one thing what I would like to emphasize at the end of this block, namely that it is one thing if we are thinking about cyber physical systems in an abstract manner. But cyber physical systems are always manifest in concrete things. And when they manifest as it is shown here, then we always have to consider errors, disturbances, deviation, and so on and so on. For instance, in case of the physical thing, physical machinery, physical plant, environment impacts or part failures and physical noise, we can consider modeling limitations or model uncertainty related to the detector sensor noise or sensor failure cases, or related to the computational resources, unforeseen load related to the network, external vulnerability, packet losses or incidental delays related to the effectors, malfunctioning may be considered, imperfect actuations, and then lack of competence with regards to the human resources or even errors committed by the human. So the functional modeling cannot take all these things into consideration, and we have to conclude. For literature, I suggest the following pieces, two from us, from our work, may be useful, from Al-Hafid and the colleagues. The high-level design of home autonomous system based on cyber physical system modeling might be very interesting for you, as well as Gans paper and the colleagues' paper on cognitive engineering, understanding human interaction with complex systems, and Huda paper on exploring parafunctional programming, separating the what from the how. These are what I wanted to mention in connection to the functional design. I'm leaving the presentation material because we have some time now for questions. Can you please go further with it? Do we have any questions? Colleagues?
No, I don't have any question. Audience, any question they can. I think if anybody has any question, they will raise hand like this, like I am doing.
Yes, but again, interestingly, that when my presentation is up, I couldn't see this sort of block of attendees, what I see now when I quit from my presentation material. So, but now, after finishing this first block, we have time for questions, short questions, obviously. So please, do you want to share anything with me? Is there anything what we need to clarify?
It's okay. It's okay, Amber.
Okay, then let me check in the chat box. What is there actually? The presentation PowerPoint is very small and not readable. And later on it became visible. Okay, thank you so much. So then this problem is solved. If there is no any other question, then and with a view to keeping the time for the recording, please allow me to shift to the second block of my presentation, and then I go back to yes.
Vijay has raised hand actually.
Sorry.
Vijay has raised hand. Vijay has some question.
Okay, please go on with the question.
Professor Imre, actually, there are number of tools for cyber physical systems at communication level, at coordination levels. So how to identify a particular tool or particular communication system for a particular problem actually?
Very good question. This is what is supported by the requirements. As I mentioned, that first of all, we need to have a definitive purpose for the whole of the system. And if this is clear and it is negotiated with the stakeholders, then you have a requirement specification. So the requirement specification is the starting point here. And based on the requirement, we can identify those sort of abstract functionalities which will be needed to fulfill the requirement. And this is how it goes. So the functional specification is preceded by the activities of requirement engineering. Does it make sense? Is it an answer, please, to your question?
Yeah, thank you. Thank you.
Excellent, very good. Anybody else from the audience? Students, please. I cannot see your face, so please be so kind when I stop with the sharing my presentation material and coming into this sort of mosaic of the images. Please be so kind for that short time, switch on your cameras because it is a more lively, and don't afraid of me, you know. It's a more lively interaction with all of you, and it gives a different atmosphere for our discussions, you know, especially when we see beautiful ladies in the screen as well. Thank you so much. If no further question, then allow me to go further with the presentation, and I share the screen again. Please be so kind to confirm if it works now. Does it?
Your screen is visible.
Okay, then I go back to the present. Oh, sorry. I go back to the presentation material and I start the second block for today, which is a kind of restricted overview of the computing technologies of cyber physical systems. Believe or not, this is the most important issue because again, we are in the stage of a technology explosion. And it means that like from a volcano, technologies are coming out, new technologies. One of the most significant thing is that not only individual technologies are emerging, but there is a kind of fusion, a synthesis of the technologies. And one of them is the so-called bang fusion, the bits, the atoms, the neurons, the genes, and the MEMS from the social technologies are coming together and they are appearing as a kind of synergetic technology. So if we have this in mind, then we can imagine that talking about the technologies is really an important issue with regards to cyber physical system. And let me give you a very brief, concise overview on the major system technologies as categories. Obviously, we can identify material technologies as relevant. We can identify powering technologies, which are also necessary, computing technologies, data and knowledge technologies, neural technologies, and also robotics technologies. And I just mentioned that we have the synergetic technologies, the bang technologies, bits, atoms, neurons, genes, and MEMS together, synergetic technology. But what is interesting that computing technologies are still the major issue now. And this is a whole issue for the developers nowadays, especially for the industrial cyber physical system developers, because so many new things came in the last 10 years. Actually, there is a jungle over there, and I would like to cast a light, weak light on this jungle, what is out there. But first, we have to see the types of digital computation. And they can be seen from three dimensions. One is the organizational, the processing, and the time dimension. Let me put it this way. From the organizational point of view, the computing technologies can be centralized computation, clustered computation, and distributed computation. Sorry, I'm too fast. While in the past, the centralized computation or the distributed computation, like grid computing, were dominating, the clusters computation have become dominant recently. With regards to the processing, we can talk about physical, embodied, embedded object computation. We can talk about abstract, structural, or sign computation. And we can talk about cognitive, mental, and interpretive computation. Each of them has various subclasses, for instance, physical computation, chemical computation, biological computation, symbolic computation, sub-symbolic computation, individual computation, group computation, social computation. So far, so good, but we also have to consider the time dimension. And from this point of view, we have to consider sequential computation, branching computation, parallel computations, and concurrent computation. So when you develop a complex cyber-physical system, the starting point is, and also this is coming from the presented functional structure, what to do with the digital computations, how to organize it, how to provide the resources, and what to do with it. So this is what I would like to continue with. I mentioned that that actually new type of computing environments are identified. We can talk about personal computing environments, which is typically a single computer which handles peripheral devices and executes all computing processing like by computer. Then time-sharing computer environment, which are which allows multiple users to use the same computing facility and share the system simultaneously by providing the time slice for them and the process and utilizes that the capability of the processors to switch from one task to the next very rapidly. Then we have client-server computing systems, which typically has one or more server, but also even one server may have multiple clients, and multiple clients request resources from the server, and the server provides them at the same time via a computer network. This is how the basic scheme of client-server computing environments can be explained. And then we have distributed computing environments, which contains typically multiple physically separated but network computing nodes and handle processes in tandem, not necessarily in parallel, but in tandem, having a part of the operating system. And then what I mentioned that this is the latest development is the cluster computing environment. And a cluster computing environment is created by merging two or more individual computer systems, which then work parallel with multiple CPUs on the same data repository. So this is there is here a centralization in terms of the data storage. It is shared, and there is a cluster forming with regards to the computer. This is how it is work. I mentioned these two things, and we have to see that there are very intense trends of developments in the field of the storage technologies, driven, for instance, by the massive data uh, processing, which is also includes the different sensor technology and sensor network technology development. So if we see the developments in the data storage technologies, then we can say that we have the so-called traditional disk type storage or the memory chip type of storage devices with their 4 to 16 terabyte information storage capacity, but these are already combined into higher level structures, which are offering 100 to 160 terabyte storage capacity, and it goes further even where these are integrated into higher units, which reach 1 to 4 petabytes, and even it goes further up to 10 to 40 petabytes. So what I described here is actually a kind of paradigm shift, starting with the units, which are organized into racks, which are organized into cabinets, and which are organized into farms. And when the farms are combined, then we have data storage forest. This is how it is at this very moment. And when we are considering industrial cyber physical system development, we have to be aware it is not about using desktop storage units or storage racks. It maybe concerns cabinets or even farms of that data storage. And then the other thing is the computing center. These are typical now. Everybody's talking about. This is again a Japanese achievement, but I could mention similar things in China or in the United States. But why I thought that it is important, but in a couple of years ago, this Fugaku named configuration was the fastest computer center in the world in Japan at a center for computational science. And what is interesting that it achieved 0.5 exaflops. So it is able to process data with that speed, enormous. And it was announced in the mid of 2020. But there is one thing what we have to see as cyber physical system developers or designers, that obviously there are these developments out there, and we have to strive after using the latest and the most capable technology. But as you could read in this call out, cyber physical computing is about functionality matching and economically affordable computer solution provisioning, rather than about unique supercomputers what no one can buy. So when we have a particular application task, we have to find the requirements, we have to specify the functionality, and then we can select that functionally matching and economically reasoning computing environment which is applicable. And what I would like to do in the rest of my presentation in this book, to tell you something about the alternatives, what you can choose from. First of all, we have already cluster computing environments. And the cluster computing environments actually a complex architecture populated on the lowest level with many terminal devices, which are actually covered by Internet of Things type of implementations. And This way, it can provide real-time data processing and analytics, data caching, buffering, optimization, human-to-machine and machine-to-machine communication. And then if we go further, there is a higher level, which is an architecting level, and then we reach where data centers and cloud services can be considered. This highest level is the cloud level. Underneath, we can identify the fog level, the fog layer, and underneath, we are talking about the edge layer. The edge layer is typically covered by the Internet of Things. But we have to identify other necessary important components in addition to the edge devices, for instance, the edge gateways, which communicate towards the cloud and the fog. And obviously, we need to identify the fog nodes, which are in one sense or other relieving the cloud layer from part of the computational and data management and data processing tasks, and also supporting the edge level. So this is how the cluster computing environments are articulated. And then the three constituents, the cloud layer elements, the fog layer elements, and the edge layer elements should be considered and will be considered in the follow-up discussion. So there is one thing what I would like to mention to you, that the positioning of the fog computing is I should say problematic even now, because many people say that it is actually not different than the edge computing, or it is also said that it is just a kind of extension of the fog, of the cluster computing towards the cloud layer. But the truth is that the fog layer is intended to provide small-scale cloud data centers, and which are located at the network edge, and this is a unique feature. So when we consider these layers and the domain resources, we can identify 4 domains for the resources. One, what I mentioned, is sort of peripheral devices, which are typically client devices. Then in the edge computing domain, we can have enterprise devices. In the fog computing domain, we can have distributed servers, and in the cloud domain, we can have centralized data centers and computing facilities. So most probably you know much more, apologize, about the cloud computing than me, but it evolved from the concept of IBM, which popped up in the 1950s related to the remote job entry processing. And actually, in 2010, it was picked up by different organizations. For instance, the first public cloud of the Amazon Web Services was also a cloud concept. And here in 2009, for instance, the NIST in the United States made a significant contribution to the specification of the cloud computing. So when we are talking about the cloud components, we can identify 3 major components: the distributed servers, the data centers, and the client computer. And the distributed servers are at geographically different places, or can be at geographically different places, but act as if they were working next to each other. The data centers are a collection of servers where application is placed and is accessed via the internet. And the client devices are with which the end user interacts with the cloud. Mobile devices, thick and thin devices. These are thick devices typically related to companies. These are related to individuals. These societies identify. Briefly overviewing cloud computing, it is a kind of self-triggering computing technology which operates with the servers and the repositories. And the main characteristics what the cyber physical system developer should be aware of, that they provide application programming interface, device location independence, virtualization, performance, and agility, security and reliability, maintenance issues are solved, and also they provide different service models. These are very important because the IPS service model is very important. So actually, we can say that there is a kind of technical component side of the cloud, the resource managers and the data managers, which are further decomposed to distributed servers and client computers and various other client computers, depending what is the goal. And then if we go into the service organization and how the services are organized in the cloud, then let me skip this because in in the slides you will see it later on. This is more about the advantages of the cloud computing. But if we consider the different types of cloud systems, then we have to consider public clouds, private clouds, community clouds, and hybrid clouds. And then when we want to organize or utilize, better to say, the service models of the clouds, then we have to consider three types of service models. One, when the infrastructure is offered as a service, it concerns the resources. The second, when a platform, a organizational platform or operational platform is offered as a service, this is what they typically call as a framework. And then the software close to the application is offered as a service. This is the application service. So the infrastructure as a service actually can be used for migrating network, server, storage facilities, as handling system resources, security gates, and so on and so on. The platform as a service can be used for web management, application development, database creation. The software as a service can be used, for instance, servicing communication, games, control systems, emails, and so on and so on. The most important thing is the remote access to all these services, and this is an important thing. Based on this, we can consider a cloud computing architecture which has the lowest layer as hardware, infrastructure, the platforms, and the applications. And here are the related services, or the provisioning, what we can have here, and actually why is it important that everything is somehow sheltered here, and what the end users are seeing, just the infrastructure as a service, the platform as a service, and the application as a service, software as a service. Very briefly, something about the edge computing and the major characteristics. You heard about that what cloud computing is doing is collecting data from the distributed locations outside traditional data centers, and then this collected data is sent to the data centers which belong to the cloud and there deposited and processed. However, with the advent of the edge computing concept, emphasis have been put on making decisions concerning computing and data processing at the place where actually the data is generated and collected, and let's try to do physically something with it. So we need for the edge computing something which is called the edge intelligence, which is the ability to intelligently distribute computing between the edge and the cloud. So the edge is a kind of step further towards making the distributed processing more rational. Why the edge introducing of the edge computing is important, because it improves or reduces the time required to make a decision based on the data, and it is very useful for applications which utilize real-time decisions, for instance, autonomous cars, which are communicating continuously. The edge computing has also a structure on its own. It has the core, it has the edge level. Actually, this is a kind of enterprise-wide computing infrastructure, and has the end devices, the PC, smartphones, IoT, other IoT devices. So these are called the endpoints. And edge computing obviously brings in the favor of locality, using local technology and diverse technologies, and the advantage of both. So what we can say is that seemingly different stakeholders and communities are involved in the use of cloud computing and edge computing. And here I just wanted to inform you about the fact that the edge computing is very confusingly presented in the current literature. At least this is my impression, because all the terms what you have here already appeared without a clear definition. For instance, what differentiates really the near edge and the far edge, apart from our intuitive view on what is near and far. So there is no clear taxonomy here and no common technology. But what is interesting that the core, the edge, and the endpoints defines a kind of data sphere, and actually it is already the current practice where core computing facilities are used for cyber physical system development, even clusters of these, which are geographically dislocated. This is very useful anyway to implement that type of cyber physical systems which are physically dislocated. And then obviously I was mentioning the role of the data center, already don't repeat it, but server tasks are, for instance, handling the client DOM demands, monitoring the traffic on the internet, and protecting safety, and so on and so on. So architecture of computing can be described with the scheme, and now I just realized that time is running faster than I can. Therefore, let me close this discussion with the fog computing, and maybe even leaving out the mobile computing, which is most probably very well known to you. So fog computing is also variously interpreted. Some people believe that it is just another name of edge computing, while others identify it as a separate computing technology. So According to my view and our view, the fog computing is a term to describe computing that takes place at distributed physical locations closer to the end users and the data sources and not in the far reach of the cloud computing. So fog computing relates to augmenting local computations of edge devices by exploiting communication devices such as routing and gateways in collaboration with the cloud. And fog computing operates by means of so-called cloud-led small-scale localized data centers and in embedded and industrial system domains, the people use the term fog to refer to computational capabilities within embedded systems and augmenting systems. So this is a kind of last emerged computational technology, but from the point of view of cyber-physical system development, it definitely needs more research. Here I summarize a couple of characteristics of computing, and also perhaps I come back to this particular slide. Sorry for the time is pressing me very much. So I would like to come back to this particular figure here, which might be interesting for you. Where is it? It's hiding here. Yes, this particular slide, this has an important thing. And if you have it, you will be able to compare the major characteristics of cloud computing, fog computing, and edge computing from the perspective of providing computing facilities for cyber-physical systems. Again, I go back to the slide sorter, and I come to the slide which contains my suggested literature. Here there are 4 items. Srinivas paper on cloud computer basics, I believe will be very useful for you. And then an overview of multi-cloud computing from Hong and colleagues are also something what I suggested to study. She and colleagues, the edge computing, Kim and colleagues, an accelerated edge computing with container and its own orchestration. These technical things like containerization and whatever I cannot talk about, although these are very useful for the cyber physical development, but in this course you have to go out and look for it. And then the fog computing fundamentals. Sorry, this was a little bit longer, but this concludes my presentation here. And then let me stop the slide sharing and let me come back to the mosaic, and let me ask you before the break, if you have, please, any question, any comments, any impression about what I presented.
Yes, sir. Hello, sir.
Please go ahead.
Yes, sir. My question is for the developing a cyber.
Can you activate your camera, please?
Yes, sure, sir. Sure, sir.
Thank you so much. Thank you. Please go ahead.
Sir. Hello, sir. Sir, my question is, while developing a cyber physical system, is it necessary to go up to the cloud computing, or we can limit it to the edge computing or fog computing? So is it necessary to go? Yeah.
Wonderful, very good question. Yes, please continue because you have a second part of the question, I guess.
Yes, sir. Yes, sir. This is what my question was.
Oh, this was the question actually. Yes. So, yes, sir, it is always the objective of the cyber physical system and the requirements for the cyber physical system. What defines the functionality, and through the functionality, the needed computing solution. You can have a node of a cyber physical system developed according to your personal or developed based on your personal computer. Tomorrow, I will show you that some of those, let's say, prototype systems, what we have developed with my PhD students were actually this type of things, even not going to the Internet of Things, or some of them were reaching the Internet of Things. So it depends on the complexity, on the massiveness, on the functionality, what you have to support with computation. Also, what is very important aspect here, the amount of data what you have to process. If this data should be collected from a sensor network, and it is a huge amount of data, then you have to consider stepping out to fog computing, or even really going out to cloud computing. But again, as I see, there is no one solution which would fit to all. This is our design decision. This is our major concerns, that how we can create a balance. As you remember, I mentioned, how can we create a balance between the need and the affordances? If we overshot with a supercomputer or whatever, we just increase the cost, but not necessarily produce economic advantages or functional advantages for operational advantages for the system. So very good. You had, sir, an excellent question. Thank you so much. This was the most essential question, actually, what you could ask at this very moment. Thank you again for that.
Thank you, sir. Thank you.
Any question by any other person? So if no question, Mr. Imre, let's take a break of another 8 minutes. We'll start at maybe another 8 minutes after that. Indian time will be 3:15. Your time will be how much? 11?
I start here at 11:45.
11:45. Oh yeah, right. Sorry.
11:45. This is where I start. Thank you so much. Have a rest, and then don't forget to come back, because the second part will also be interesting.
Thank you. So we'll meet in within 8 minutes.
Exactly.
All Indian students, Indian people, 3:15 p.m. sharp. Thank you.
Thank you.
Welcome back, Imre.
Hello.
Yeah, hello.
I am here, just made a little modification on the setup. And
Okay.
now it's okay again. We can start. I'm ready for sharing the screen.
Okay.
Just a moment.
You can start now. So all the participants, be ready.
Yeah, so let's start with the second lecture for today, which is about the generations of cyber physical systems. This lecture is decomposed into two blocks. The first one is introducing the concept of generations, and the second one will focus on the so-called second generation cyber physical systems, and in particular on the smartness as a concept in systems rather than in human beings. So the title of the first book is a evolutionary view on cyber physical systems. And obviously some 15, 10 years ago, we were considering the paradigm of cyber physical systems. And at that time, it just emerged. And later on, a couple of years later, we observed that actually it is rapidly developing, and different opinions about the essence of cyber physical systems were published in the literature. And this is why we consider that here a kind of out of the box thinking is needed. And what came to my mind and described the situation is a kind of quote from Erwin Schrödinger, who said that the task is not so much to see what no one has yet seen, but to think what nobody has yet thought about that which everybody sees. So what does it mean? Everybody was dealing with the cyber physical systems, but their evolution was not considered in the thinking. So this is an important observation because, for instance, this was the stimulus for us to introduce a new definition different than the then mentioned popular definitions. And we identified the distinguishing characteristics of cyber physical systems. Yesterday I presented it: smart multi-actor network systems enabled by cyber physical computing, deep diffusion in physical processes, sensing, reasoning, adapting, and actuating loops, model of future intellectualized system, resource and service provisioning, and application opportunities in human and social context. Obviously, these characteristics are neither all or none, and also not perpetual characteristics. They can develop as cyber physical systems are developing, pushed by science and pushed by technologies. So what we assumed was that cyber physical systems will develop so-called paradigmatic generation. We were aware of the fact that it is very difficult to demarcate one stage of development from the next one. but we wanted to make a characteristic separation for the generations, and this is why we thought of certain things which really make significant difference, if you like, draw a demarcation line between the concepts. And we consider two basic enablers, and these were derived based on a kind of analogical argumentation that if you consider the human and what happens with the human, then we have the body, the physical part, we have the brain, the let's say the cognitive part, and then the brain part, the cognitive part, support us in the self-intellectualization. So we are becoming more clever, let me put it this way simply. And the other part, the body part, is about the self-organization aspect. And obviously there are multiple interactions on multiple levels between that, but we could use the levels of self-intelligence and the level of self-organization as a kind of ordering principle to talk about generations of cyber-physical systems. Here I have to note something. Obviously, many people, even at conferences, ask me that why consciousness is not considered as a fundamental thing related to cyber-physical systems. I tell you frankly that there can be two answers to that. One is that we don't know enough about consciousness, in particular not about that version of the consciousness which is implemented in artificial systems. And the second one, that philosophically we don't know yet if a very late generation of cyber-physical system would need consciousness. Contrary to the fact, I will discuss some aspect of it tomorrow in my presentation. And then people also ask us that what is with autonomy? And then we say that if these two are there, the self-intellectualization and self-organization, they provide the basis for a kind of autonomy. So the autonomy is not a fundamental, but a derived characteristic. So based on this explanation, let me introduce you operational modes, what we identify. We are talking about reactive operation when something is just effectuated when something happened and detected. We can talk about anticipating operation. We can talk about cognizant operation. Cognizant means that awareness with understanding. This is how I use the term. And then we can talk about intelligent operation. If it is true, then the reactive operation with regards to the cyber-physical systems can be defined as self-regulation and self-tuning. Self-regulation in the intellectualization and self-tuning in the organizational domain. Likewise, anticipating operation, self-awareness and self-adaptation. Then cognizant operation, self-understanding and self-evolution. And then intelligent operation, self-consciousness if needed, self-autonomy, and self-reproduction. Obviously, intelligence and smartness are two different terms, and we also respected this differentiation. And we considered smartness in our work as a addressable pragmatic quality of human thinking and feeling, doing and making, and as it can be converted to cyber-physical systems. Later on, I will revisit this issue in detail. So when we are talking about the generations of cyber-physical systems, our model is the following. These are the true trajectories of self-intellectualization and self-organization, and these arrows are showing the level and the changing level. What we have in the base is the physical systems and processes, which are sensed and they are changed, and the change is introduced through some kind of actuator. What is essential here, not this very simple basic thing, but how these sort of things are done. And recall my figure from the previous slide. That explains what we can put here and what we can identify as generation of cyber physical systems. So first of all, we have the so-called we identified them zero generation cyber physical systems, which are localized or incomplete systems, and they are able to make supervised execution and external adjustment. Consider, for instance, the control device in your washing machine. Then the second level, actually, the level of the first generation cyber physical system, which are able to regulate themselves and able to tune themselves. Then comes the second generation in our definition, which includes systems which are able to build self-awareness and which are able to adopt themselves. The third generation cyber physical system, according to our interpretation, are those which are understanding what is happening with them. Question obviously what understanding in this context means, but definitely achieve some sort of self-evolution. And the fourth generation, the last one, which might approach a kind of meshing self-consciousness and also a reproduction. But this reproduction is not a biological type of reproduction, but a reproduction which considers the objectives and the available resources and works with them. So this is our model, which reflects the generations of cyber physical systems. And at this time, we can focus on the second generation of cyber physical systems, which are often referred to as smart systems. So before going into these things or analyzing the concrete generations, let me tell you that based on the publication and based on the reflections, what we found why this framework is useful were different things. For instance, we found that it is useful from an ontological point of view because it provides a straightforward and robust categorization of the various contemporary and future implementations of the CPS. If really the CPS are developing and evolving, then we need this robust categorization. Then from an epistemological point of view, it helps creating a logical relationship between the paradigmatic system features and the categories of CPSs, but obviously without considering human aspect through the system knowledge. And then the methodological point of view should also be mentioned here, because it suggests a kind of roadmap if you consider the evolution through the generations. So it suggests a roadmap for the CPS development and emphasizes truly transdisciplinary approaches that address synergism in this sense. And then there is a pragmatic point of view here, which I need to mention, namely that this model radiates the need for more research and knowledge about transferring cognition from human to complex system, because as you see that beyond this more system, the second generation system, we have empty, if not completely unknown spots, you know, for instance, related to cognizance or related to manifestation of consciousness in systems, and also the theological issue, why systems do need it, and so on and so on. Later on, I will talk about these effects. So very briefly, let's see what are the characteristics of these different generations. The zero generations, as I briefly mentioned, include lookalike engineering system and partial recursory implementations of CPS. They are incomplete realization of the possible CPS functionality and program behavior. They can be such as embedded hardware and software systems, software integrated process monitoring systems or control systems, Internet of Things systems, complicated production systems based on the traditional control principles, and so on and so on. Typical industrial representatives of zero generation cyber physical systems are so-called plant type of subsystem, continuous operation, set working target, and typically deviations from this target. But also monolithic artifacts can be considered here, such as advanced robots, for instance. Important to know that for the zero generation of cyber physical system, the control can be seen as pre-programmed, typically generated based on the principle of classical hardwired control theory. And there are no resources for situation-dependent reasoning, learning, and training. So the zero generation system cannot deal with these sort of things like situation-dependent reasoning or learning and training. Then let's see the first generation, in which sense they are different. So this is the first true implementation of the cyber physical system paradigm, according to our view, and what makes them as such is the capability of self-regulation and self-tuning. First generation CPSs are closed systems and often referred to as common software integrated systems. They include components that collect sensor data and react on them by using control signals via actuators. Self-regulation is exemplified by feedback type control in this system. So the control subsystem is neither adaptive nor predictive, but needs to cope with dynamic phenomena of software and hardware. Because even the first generation of cyber physical systems are supposed to operate in dynamic working environments. So the control systems are problematic, especially when adaptation is needed for meeting these expectations. So they can allow only very restricted functional or architectural adjustment. This is what they can provide in the framework of self-tuning. And this is something like happens with the resilient systems, which are functionally enhanced in operation. But again, like with the zero generation cyber physical systems, these systems do not possess resources for adaptation, and they cannot plan adaptation. They cannot change the objectives of operation, and because they miss the learning and reasoning capability. And then perhaps the most important generation for us for the current time being the second generation. And the second generation was characterized in my model or our model by self-awareness and self-adaptation. So this is a serious step towards intelligent or smart behavior. Second generation cyber physical systems capture data related to local worlds. They interpret purpose and task. They interpret context and situation. Based on that, build awareness and develop or change operational models. In order to make adaptation possible in this system, they typically need to have access resources which are not needed in a particular operation, but might be or may be needed in a different one. So these resources should be something accessible for the system and should be easily rearrangeable, replaceable. They should be combinable and interchangeable. On component level, it is typically achievable, but we face problems when we are talking about higher level functionalities and modules and subsystems. Second generation CPS use runtime acquired data in addition to the data stored in the system's operational model. So most of the second generation systems do have a system model, an operational model of the system, and also a control model. They store data, but in addition, the system collect runtime data, and that causes further challenges for their operations, as you see later on. The adaptivity, the capability to adapt themselves according to the environmental effect, or dynamics, means that their adaptivity depends on the variety and the number of components, interfaces, as well as on the degree of connectedness. A strongly connected system is more difficult to adopt than a loosely connected system. A system with extremely large number of components and interfaces more difficult to adopt than one with less. So what is interesting that in a second generation cyber physical system, there is a built-in increased reasoning, planning, decision-making capability. These features together result in that sort of smartness which is expected as a operational capability. However, there are no capabilities for understanding and abstraction in this system. Now, if we go to the third generation, immediately we project into the future. Obviously, it means that we have less concrete and tested knowledge about that, more assumptions. But on the other hand, I believe that there are already trends which show which direction we go and what will the essential feature, paradigmatic feature, or set of features for the third generation cyber physical system. As I mentioned, one of the issues is the self-cognizance. Cognizance in this case is understanding, comprehending what the information means in that particular context when it is used. And the other issue is the self-evaluation. In the field of software engineering, self-evolution is intensively addressed at this very moment, as I know from colleagues. However, the self-evolution issue is still somewhat limited, known in the context of fully featured cyber physical systems which do have hardware, software, and cyber components. So when we are talking about cognizance, we suppose that it enables the development of runtime models of the system operation and working environment. If the system understands what is happening, then they may be supposed to develop runtime models which control themselves. Obviously, there are already pre-developed and runtime adaptable models, but this would mean developing models from scratch. And this cognizance for this purpose assumes semantic insight of the problems and tasks. What is to be solved and what sort of tasks are helping to solving this or help solving this problem. I would like to emphasize that it is becoming prohibitively difficult to predict all future operating scenarios and environments and designing three-generation cyber-physical systems. The time has not come yet for that. But the evolution, as I mentioned, is already addressed, and the evolution is implemented by subsequent extension of the operational domain of the system dynamically in various contexts. This can be done with software tools because software tools can be downloaded or uploaded on the internet, obviously, and the cyber physical system can identify and operationalize the software tool. But what is with the physical things which are also there in the cyber physical system? This is a challenge. So we believe that cyber physical system, contrary to these uncertainties, can be designed to evolve or do it in a kind of non-predefined way, making decisions on it by themselves. On the other hand, it is fair to say that system evolvability is still an unexplored field related to cyber physical systems. In the literature, it tells me the total number of papers which are available addressing the fully fledged system evolvability related to cyber physical systems. So we see that the whole self-evolution program should be addressed not only from the perspective of the software engineering, research and development, but also considering the total resource management issue. And now, the fourth generation of cyber physical systems. So they are even just in the far side. We don't know what will happen over there actually, but self-consciousness and the capability of self-reproduction may produce surprising facts for us. They will be based on integrated matter and mega models and full-scale implementation of system intelligence. We will talk about it later, what systeligence means in this context. Rating intelligence of fourth-generation cyber physical system based on how well they are substituting or replicating the intelligence what the humans are having is, I believe, misleading, but also illogical. Fourth-generation cyber physical systems by us not seen as replacement of humans or whatever, but something which expands the human capabilities both in the physical, in the cognitive, and in the semantic domain. No real work has been done concerning consciousness at this very moment, closely related to the fourth generation cyber physical system. I will talk about it later on, why there are many pretensions with regards to intelligence. Sometimes intelligence is misused, overused, and misleadingly used. So we assume that first generation cyber physical system need to reason about the manifestation of functionality with an external view, teleology issue. They should be able to decide on what I want to do. But this is a teleology. And I also have to mention that there is a debate about the social and economic role of self-replicating systems. Is it utopic? Future tells. At least we have a model to reason about it. Several times I mentioned that intelligence is associated with artificial intelligence. At the end of this book, I have to say and refer to a book in which I read something, it is titled What Robots and AI Learn in 2015 from now. And I read that artificial intelligence might be the most apocalyptic technology of all. So this is how I would like to close this part, and we will revisit it later on in the follow-up lectures. But to deepen your knowledge, I suggest this particular paper, actually, in which we introduced the concept of generation at the ASME conference in 2017. I also recommend you to read this paper of Rajkumar and the other authors related to cyber physical systems, the next computed revolution. This paper, conference paper to us, independent in-cloud evolution of cyber physical system, cast light on the expectable self-development. And the last paper is about enabling self-adaptive workflows for cyber physical systems. Thank you so much. This concludes the block. I close the presentation for the time being. I stop sharing, and I'm very curious about your questions, please.
Hello, sir. It was a nice session, actually. Sir, as you
Yes,
you
please.
told us that there are 4 generations of cyber physical systems, and currently we are in the 2nd generation. So all these systems like cyber physical system like smart grids and robotics must be in 2nd generation of cyber physical systems. Sir, I am curious to know if there is a real life example of 3rd generation cyber physical system. If it is applicable, can you please?
Very good point again. Please allow me to say something to the explanatory part of your question. So what we have now, not only 2nd-generation system, what we have now is the coexistence of 0th-generation, 1st-generation, and certain 2nd-generation systems. Second-generation systems are still in development. We know much more about the so-called 1st-generation cyber physical systems, but much less about the 2nd-generation systems. In the next block, you will hear, please, about, for instance, the problematic of understanding smartness, how to reproduce human smartness in this cyber physical environment. When you ask me about a typical example of 3rd-generation cyber physical system, and if I would connect it to that particular video, I don't know if I believe you saw the video, what I projected earlier. So it would be a kind of operating theater which makes decision in face of the humans about what sort of medical operation, medical treatment is needed. Because here is the cognizance, understanding that why I am there, not just doing what based on logic, based on smartness I can do, but also figuring out that what I need to do or what I can do at all in that particular context. So I can imagine if this operational theater is equipped with these and many other capabilities, then they can go into this direction. And let me consider the self-organization aspect as well as a response to your question. What I said that actually self-evolution. So let's consider that the system is not just dealing with problem solving in the context of the operational theater, but it also monitors how well the devices, the resources, what it had operated in the past, the hardware, the software, the cyberware, and it improves them based on data. It can be done by the system, or informs the system developers that these enhancement opportunities are out there. So either the increased autonomy based on cognizance, or the evolution based on generating more resources can be the pathway to third generation cyber physical system. So we don't have these sort of things yet. This is why I always get a bit confused when people are writing about intelligent cyber physical systems. What does it mean? Thank you so much for your question, sir.
Yes, sir. Got it, sir. Thank you.
Any other question anyone has?
I believe if no more questions, we can shift to the next block for today.
So,
and then I go to screen sharing again, and I reactivate the second part of my presentation. Which is about elaboration on the second generation cyber physical systems. I believe the recording is on and I can go further.
yes, you can go further. The recording is on.
Thank you. So this block will be about the understanding of smartness of second generation cyber physical systems, because this is how we define them as smart intellectualized systems. But the question is that what smartness means. I already mentioned that that in fact I have trouble to understand the word intelligence with regards to system. But also the smartness is something what is interesting, because when I studied the literature, I just realized that it is again the Indian elephant case, where depending on where they contact the elephant, the people do have different observations and they believe this is smartness. I'm not saying, not claiming that that sort of interpretation of smartness, what I'm presenting here is the overall, but at least it might be useful for you to have a kind of insight in the system level manifestation of smartness. And I have to go back to the history, because when I attended the university at the 70s, actually I came across with the notion of smart systems at that time, and these sort of integrated microprocessors were called smart systems at that time, and still this exists. And then in the 90s, internet came in, and internet was considered as a kind of smart solution because it was supposed to provide semantic content repositories. Then later on, in 2000, from 2006, cyber physical system equipped with reasoning capabilities are considered by many people as representative of smart systems. But obviously we can go further because in the last years, actually the concept of intelligence and the board concept came in as focused problem solver. So here is also a historical problem with the notion of smartness and understanding of the smartness. So again, we have to come back to the human behavior in order to define what it is and what we can accept as a starting point. So smart is a carelessly overused general term, and therefore we have to see what does it mean in the human behavioral context. Behaving with above average logical reasoning skills and successfully applying them to solve technical, scientific, social, economic, and political problems, and having pragmatic, emotional, and ethical concerns. This is the most extensive definition what I so far found on the internet about the human behavior and the smartness of human behavior. So in a nutshell, it implies two things. First of all, that smart humans are better problem solvers than others. We have to project this also to systems. And the second is that what helps better solve a problem also makes smarter. So learning from the solved problems, it is also an element of the smartness. It's fine so far, but what does it mean for designing and for developing systems? So in fact, there is a kind of consensus in the literature that the core of the smart operation is a quadrant which includes the operation of observing, reasoning, learning, and adopting. This led us to the definition of the second generation cyber physical system. Here, hardware sensors, software sensors, mixed sensors, data hybrids involved in the observation. The reasoning, system level models, dynamic context representation, inferring reasoning mechanism, data knowledge bases, and ontologies are considered. With regards to learning strategies, artificial intelligence algorithms, semantic interpreter, runtime planning capabilities, and related to the adaptation, analog devices, robotic manipulators, programmable actuators, effector networks, control instruments, these are all involved as resources for this sort of smartness loop. When we consider this loop, actually, we can say that this already implemented in many commercial products which are referred to as smart systems because this loop, the interfaces, sensors, data receivers, knowledge-based management, actuation of cognitive mechanisms, and the actuation of physical operation and data transmission are already present in your mobile phone. Everybody knows it. I don't want to spend more time on it. But we have more complex issues related to the use of smartness and the smart operation in systems, especially in environment, and the smart built environment is supposed to have efficiency and healthy operation, renewable and energy uptake, responsive energy systems, dynamic self-learning and control opportunities, and dynamic operational. So it is an extension already what I showed in my previous slide. The most important thing is that what we can find in the literature related to the smart built environment, which are also approaching the second generation cyber physical system, that as a kind of threshold or minimal requirements, the key factors are connectivity and networking capabilities, operation under self-control or even semi-automatism or autonomously, context-sensitive interaction with users and devices, low consumption and environment friendliness, and relying on cloud infrastructure and services. Okay, this is what the literature says. We were talking about the computing facilities already. We will talk about context processing issues and also the networking issues later. So if you look into the literature, you also find that actually there is an issue related to the design of smart approaches as problem-solving competence, how the problem-solving competence can be built into these devices. And there are three doctrines for it. The simplest one is actually a smart augmentation. If these are connected on a house level or a region level, obviously this is a step towards smart system. Smart integration as a second approach, it is clearly appearing in cars and vehicles. And the third one is the smart automation. I believe this will be the most important for the future, but uh, uh, at this very moment, the real representatives are not more complex than, let's say, smart automation or smart grass cutters of the smart automation. So based on this, nevertheless, we can have certain characteristics of smart system defined. And one of them is the personalization, customization according to the stakeholders' need. The second is the awareness, which means considering objective states, constraints, and context. Situatedness, which is a recognition of the situational and community context, the state, for instance. Adaptiveness, rendering behavior to objectives and conditions. Connectedness, the ability to communicate, integrate, and bonding. And proactivity, anticipation of stakeholders' plan and intention. This is obviously something which triggers the need for adaptation. So these are those characteristics what we believe important to consider at the development of second generation cyber physical systems. And then let's revisit that sort of computational smartness issue, what I presented very briefly as the four interacting board. So what I drew there was not actually correct because it is not just one circle, it is not one loop, but a kind of spiraling and returning. And here, obviously, what we need is the multi-source sensing with those sort of elements what I already mentioned. We need also building awareness for the cyber physical systems. Then we need an ampliative reasoning. Ampliative means in this context that when the reasoning happens, we more known than what was previously programmed. This is the essential thing of ampliative reasoning. A rule-based reasoning is, although useful, is not ampliative because we will know more, but a deep learning is definitely ampliative reasoning. And then a strategic learning, learning to ask the goals, and the operation planning is also an important element here. And finally, the implementation of the runtime adaptation. So if we want to implement a smartness cycle in the operation of our cyber physical system, then we have to consider this spiraling. So the first time, maybe we don't have a optimum result, but when we refine the things, when we refine these components, then we have a higher level smart. So smartness is also evolving capability, and we have to treat it like that. But there is one more important thing because of system smartness. And before finishing this module part, I would like to elaborate on this, namely on the dual space of smartness. And it goes back to the very simple question. Can we recognize if someone is smart, a human being is smart or not? And then we say yes, because this particular individual is able not only to solve the problems, but also looks like smart. So the external world should be aware of this that something happens here which is element of a smart behavior. This is the dual space of smartness. And then obviously everything related to the cyber physical system, what I just explained, should be put here. But also these two spaces, mainly the operational space and the observational space, where the non-functional capabilities are also observed, are multiple, connected to each other with multiple types. And for instance, we can decide on the smartness of the system if it is convincing. Do you see it really intellectualized? The second thing, is it dependable? If the smart system can solve the problem as it does, do you dare to depend on it? Then is it dexterous? Do you really see that all the logical and physical capabilities are operationalized in order to achieve the solution is in the most rational way? And then is it trustworthy? Is it really something what you can accept as a strategy, as a kind of solution? So this is the dual space of smartness, which I believe those who are dealing with second generation cyber physical system development should consider. And then I mentioned the aspect of characterization of smartness. But when we design smartness, we have to accept the fact that certain things can be more operationalized than other things. So actually what we implement or can implement in the praxis is not a ideal implementation currently with smartness. We can define a desired extent of smart systems, and then what we can strive for a balanced capability of the smartness profile of the system. But this is a challenging issue, and this is where we need to do more research. So when I'm talking about the challenges of smart cyber physical systems, I have to say that the smart system operation cannot be completely defined. There is an emergent behavior there, and the smart operation needs self-reasoning, self-learning, self-adaptation, and self-evolution. And the challenge is how to develop those sort of contemplation mechanism and how to harmonize them on system level. I mentioned that focused research is needed, and also the most important thing is for us to see that the best if we just think of tailored problem solving intellect rather than general intelligence in these systems. Before closing, I would like to recommend you to have a look into the book of Gardner, which is the intelligence refrain. Later on, we use parts of it. Then this sort of editorial, what I co-authored with some colleagues, the smart designing of smart systems also can be also informative for you. And then I read this paper, the not too far away path to smart cyber physical systems. And then with one of my recent PhD students, we published a survey which is about the state of the art of reasoning framework development for smart cyber physical systems. And this is the paper of my respected and kind professor colleagues from Belgium, Danny James, who is one of the gurus in self-adaptive and self-evolving software development, and I recommend their literature review on self-adaptation for cyber physical systems. Thank you so much. This concludes this part of the presentation. This was what we were hearing about the paradigmatic generations and also the concept of smartness we discussed. Thank you for the attention. I stop the screen sharing. I go back to the communication mood, and please be so kind to put forward if you have any question, comment. Was it clear? Was it useful? Was any new things included in this at all for you? Please be so kind to comment. Anybody who didn't say anything, for instance, until now yet, for instance, Mr. Ravat or Raj or whoever, please just open your camera.
So I personally enjoyed a lot today's lecture, but I think it's up to the participants, the students, who can give a better perspective of the today's lecture.
Sure. But as I mentioned to you, and as we were discussing it, it is very difficult to have a presentation which fits all the students, especially because you kindly asked me to talk about the very new things, those sort of things which are not yet published in papers, which are not yet presented at the conferences, which are actually just shared between the experts, you know. So this is why I believe the participants of this course will be in a delicate position, having heard all these new developments and being well equipped for the coming, let's say, 5, maybe 10 years. Who don't know? Who don't knows? I don't know.
So anybody want to put any comment or any suggestion?
Thank you so much. Then I believe this concludes.
Just hold on. We have to take one picture. So
Yes.
I'll request all of you to kindly switch
Please open, please open the camera if you would be so nice.
all of you, please open your camera.
All of you, please, yes.
Harshal, Ishant, Sandeep, Mithilesh, Ankita, Swati. Please open your camera. Mithilesh, you can go to your screen also.
Sir, his system doesn't have camera.
Okay, no issues. Vijay, Ishant.
Yeah. Okay, thank you. This was for today.
Just once. Ishant, are you there?
Yes, sir. So there is an issue, sir.
Please open your camera. Sandeep, Ankita and Swati. Please open your camera. Okay, then we can take a break for 15 minutes. And as we have discussed, we'll start again at 4:30 p.m. Okay.
Thank you so much, and thank you for the attention. Especially, I appreciate very much the excellent questions of Mr. Vasanta. Excellent, sir. I really could have the impression that you deeply followed the presentation, and let me congratulate you for this involvement and then for this openness and contribution. Please continue with the practicum part, and see you then tomorrow morning at 2 p.m. for you and 10:30 for me here in the Netherlands. Have a good time. Bye-bye, and thank you for the attention again. Bye-bye.
Take care. Please take care. Bye.
Thank you. Bye-bye.
So I'm